Welcome back to Fun Facts Online. Today, we are stepping away from the hype cycles of standard tech news to look at a fundamental shift in how machines think. We are going to talk about the silent revolution happening inside the microchips of the future. We are talking about spiking neural networks, or SNNs. To understand why this matters, I want you to visualize a modern data center. Imagine standing in one of those cavernous server halls. The air is vibrating. It hums with the sound of thousands of fans trying to cool down thousands of GPUs. These silicon engines are crunching numbers in massive matrices to power everything we use today, from ChatGPT to self-driving cars. They are brilliant, they are capable, and they are voraciously hungry. To train just one state-of-the-art large language model today consumes as much electricity as a small town does in an entire year. Now, compare that industrial roar to the 3-pound organ sitting inside your skull. Your brain manages to write symphonies, calculate the complex trajectory of a tennis serve, process emotions, and regulate your heartbeat, all at the same time. And it does all of this on a power budget of roughly 20 watts. That is less energy than a dim light bulb. For decades, computer scientists have looked at this disparity with pure envy. Why is biology so much more efficient than silicon? The result of that envy is a technology that has finally, in the years leading up to 2026, graduated from the laboratory to the real world. This is the world of spiking neural networks. Unlike the deep neural networks that dominate the headlines, SNNs do not just loosely inspire themselves on the brain, they mimic its fundamental language. They don't calculate in continuous flows of numbers. Instead, they communicate in pulses, spikes, and events. They are the third generation of neural networks, and they promise to sever the iron link between artificial intelligence and massive energy consumption. To understand why SNNs are revolutionary, we first have to understand the inefficiency of traditional AI. We need to look at the problem of loud AI. Imagine a security guard watching a monitor displaying an empty hallway. In a traditional deep neural network, which is used by most standard computer vision systems today, the AI analyzes every single pixel of that empty hallway, frame by frame, 60 times a second. It continuously shouts to the processor, "Nothing is here, nothing is here, the wall is still white, the floor is still gray." It processes data even when absolutely nothing is happening. It is a loud system, constantly burning energy to reconfirm the status quo. A spiking neural network operates differently. It acts like a biological eye. If the hallway is empty, the SNN is silent. The neurons are dormant. They consume almost no energy. But the moment a person steps into the frame, the pixels detecting the change spike. They fire an electrical pulse. The network wakes up instantly, processing only the movement, only the event. This is called event-driven processing, and it is the heart of the SNN advantage. In a world drowning in data, SNNs teach machines the most valuable skill of all, which is the ability to ignore what doesn't matter. Let's get into the physics of how this actually works. At the core of an SNN is something called the leaky integrate and fire neuron model. It is a mathematical approximation of how your own neurons function. It works in 3 steps. First, there is integration. The artificial neuron receives electrical signals or spikes from its neighbors. It accumulates this charge, like a cup filling with water. Second, there is leakage. If no new signals come in, that charge slowly dissipates. It leaks out. This ensures that old, irrelevant information fades away, which is a crucial feature for real-time processing. Finally, there is firing. Once the accumulated charge hits a specific threshold, the neuron fires. It sends a single, sharp spike down its connection to other neurons, and immediately resets its charge to 0. This binary, all-or-nothing communication is radically different from the continuous decimal numbers used in standard AI. It creates sparsity. In a typical spiking neural network, at any given moment, 90 to 99% of the network might be inactive. This sparsity is where the massive energy savings originate. Furthermore, SNNs introduce the dimension of time into the neural network equation. In standard AI, the order of inputs in a static image doesn't matter temporally. The whole image is processed at once. In SNNs, the timing of the spike carries information. A spike arriving 2 milliseconds before another can mean something entirely different than if it arrived 2 milliseconds later. This makes SNNs inherently superior at processing temporal data, like video, audio, vibration, and radar signals. Software is only half the battle. To run a brain-like code efficiently, you need a brain-like chip. We are currently witnessing a Cambrian explosion of neuromorphic hardware, chips designed specifically to execute these networks. As of late 2025, the giants of the industry are making big moves. Intel has continued to push boundaries with its Loihi architecture. The latest iterations, Loihi 2 and its 2026 successors, have moved beyond research curiosities. With millions of neurons packed into a single chip, They are now being used to solve optimization problems that stump classical supercomputers, like routing railway traffic or optimizing financial portfolios at a fraction of the energy cost. Then you have IBM's North Pole chip. It has redefined efficiency by eliminating the von Neumann bottleneck. That bottleneck is the energy-wasting shuttle of data between memory and processor that slows down traditional computers. North Pole intertwines memory and computation, just like the brain does. But while giants build supercomputers, agile startups are putting brains into edge devices. SNNs has emerged as a titan in the low-power vision space. Following its strategic consolidation with innovation, SNNs now dominates the neuromorphic vision market. Their chips are not sitting in server racks. They are in toys, smart home hubs, and even smart husbandry devices. These are collars for livestock that monitor health and behavior by analyzing movement patterns in real time for months, on a single coin cell battery. Another key player is Inotera, a spin-off from Delft University. They made waves in 2025 with the spiking neural processor T1. This chip is designed for the sensor edge. It sits directly next to microphones and radar sensors in wearables. It allows smart headphones to filter out background noise using SNNs to distinguish human speech from traffic, reacting in microseconds without needing a connection to the cloud. And we cannot forget prophecy. They have revolutionized the eye of the machine. Their event-based metavision sensors are neuromorphic cameras that do not capture frames. They capture changes. If you shoot a spinning fan with a prophecy camera, you don't get a blur. You get a crisp stream of spikes representing the moving blades. This technology has become the gold standard for high-speed industrial inspection and autonomous driving. A critical piece of this puzzle is memory. Weebit Nano has successfully commercialized ReRAM, or resistive RAM. This is a type of non-volatile memory that functions remarkably like a biological synapse. By integrating ReRAM with neuromorphic circuits, engineers can now build hardware where the learning, specifically the changing of synaptic weights, happens physically in the memory cell itself. This further closes the gap between silicon and biology. So where is this actually being used? The theoretical phase is over. SNNs are deployed in the field, solving problems where standard AI fails due to power or latency constraints. One of the most critical areas is the autonomous nervous system in cars. In the race for autonomous driving, reaction time is everything. A standard camera running at 30 or 60 frames per second has a blind time between frames. At highway speeds, a car travels blind for meters during those intervals. Mercedes-Benz, particularly through its Vision EQXX program and partnerships with the University of Waterloo, has bet big on neuromorphic computing. By using event-based cameras and SNN processors, their driver assistance systems can react to a pedestrian stepping off a curb in milliseconds, orders of magnitude faster than frame-based systems. Furthermore, because SNNs are so energy efficient, they extend the range of electric vehicles by reducing the massive power drain of the onboard flight computer. We also see this technology in orbit. Space is the ultimate energy-constrained environment. Solar panels provide limited use, and radiating heat away is difficult. In 2025, NASA's Beyond the Algorithm Challenge highlighted the agency's shift toward neuromorphic solutions for Earth science. Traditional satellites capture massive images and downlink them to Earth for processing. This is a slow, bandwidth-heavy process. SNN-equipped satellites can process data in orbit. For example, a satellite monitoring for forest fires doesn't need to send terabytes of images showing no fire. An onboard SNN can monitor the visual stream in low-power sleep mode, spiking only when it detects the specific visual signature of smoke or flame, and then instantly beaming a high-priority alert to ground stations. This concept is evolving into the Space Computing Power Network, where satellites act as a distributed, intelligent mesh network above the atmosphere. Even further out, we have the Mars drone problem. Flying on Mars, where the atmosphere is thin, requires spinning rotors at incredible speeds, draining batteries rapidly. Every milliwatt saved on computing adds seconds to flight time. The Parallax Martian Flight Project utilizes neuromorphic processors for motion estimation. By processing visual data using spikes, the drone can navigate and stabilize itself with a fraction of the power required by the original Ingenuity helicopter's traditional chips. Perhaps the most exciting development of late 2025 is the hybridization of SNNs with the architecture of large language models. For years, SNNs struggled with accuracy compared to deep learning. You couldn't simply chat with an SNN, but researchers have recently cracked the code on spiking transformers. By converting the attention mechanisms of transformers into spike-based operations, scientists have created language models that are 10 to 20 times more energy efficient than their standard counterparts. This is the breakthrough that will eventually allow a ChatGPT-level assistant to run locally on your smartphone without draining your battery in an hour. It is a quiet LLM, activating only the specific neurons needed to answer your specific query, rather than lighting up the whole network. Despite these triumphs, the road to a fully neuromorphic future has speed bumps. We still face the training dilemma. We don't know exactly how the brain learns. Standard AI uses backpropagation, a calculus-based method that requires continuous numbers. Spikes are non-differentiable. You can't do calculus on a sudden step. Researchers use surrogate gradients to smooth out the spike for the math, but it remains a complex process. Then there is the conversion tax. Many current SNNs are just standard artificial neural networks converted into spikes. While efficient, they often lose a bit of accuracy in the translation. The holy grail of networks trained directly in the spiking domain to learn temporally is still an active research frontier. As we look toward 2027 and beyond, the line between biology and technology is blurring. We are moving from artificial intelligence to organoid intelligence, computing systems that don't just mimic the brain, but might eventually incorporate biological components. But for now, spiking neural networks represent the most significant shift in computing architecture since the invention of the transistor. They are teaching our machines to listen to the rhythm of the world, rather than just the volume. They are proving that in the quest for true intelligence, silence is just as important as the signal. Thanks for listening to G Fun Facts Online, and stay tuned for the next revolution.